Okay, so in section 13.2, we're going to focus in on dynamic programming for joint space planning. So the question that we're interested in answering is, what may be the best joint space solution when we have numerous IK solutions? And what we're going to look at here is a dynamic programming solution for robots with low dimensional null spaces. So if we have a 7 degree of freedom arm and a 6 degree of freedom control space, then we only have a one-dimensional null space, and so it's a null-dimensional null space that we're working here, and this solution will work for those situations. Let's recall that in our previous example, we sampled 61 Cartesian points. Then for each of those points, we had a range of 130 to about 285 IK solutions, but we could only accept one of those solutions. So we wanted to optimize a smooth trajectory, right? That means we need to avoid discontinuities. Discontinuities means that we would change the motion of the robot in a drastic way. We would jump quickly from one configuration to another. Now, to have a smooth motion, we cannot select a joint solution for a waypoint independently from solutions for other waypoints. This wouldn't work. We need to study how the robot is moving throughout all of these points. Just looking one step ahead, we would say is naive, not deep enough, and it will lead to discontinuities eventually. This doesn't work. So basically, we are forced to look at the entire trajectory together to find the optimal sequence of points. So the way dynamic programming works for this is as follows. Consider an example where we have 6 layers in a graph. So this would be a 6-layer feed-forward graph. For each of the layers, we would have a number of nodes. These nodes can be encoded by their layer number and then their row number. So for example, in this first layer, we have 3 nodes. And so this would be N11, N12, N13. And what we're interested, also these layers would represent a Cartesian pose for a given waypoint. So what we're interested in looking at is a path through each of these layers all the way to the end. So here we would have a starting point pose somewhere here and an ending pose here, and we want to know what's the best path through the graph from beginning to end. Each and every single one of these paths is associated with a cost, okay, a cost C. So that path cost is really going to be the sum of the cost for states at given layers and rows, and also the sum of the transition costs from one node in one layer to another node in a different layer. Okay, and as I mentioned before, that layer represents a 6 degree of freedom task space pose, which would be a sub-goal. And each node, M, can represent a different joint space inverse kinematic option. So a solution for pose L and solution M is just this N sub LM, right? And we're looking for that sequence of nodes, one per layer for the graph. So how do we assign costs to a state or costs to a transition? Well, we could think that any pose that results in a collision with self or in the environment would have an infinite cost. Of course, this step would involve the inclusion of a collision detector or collision planner to help you identify whether or not you're in collision. ROS has advanced techniques. ROS incorporates advanced techniques for collision detection that could help you resolve for this. Also, poses that result in near collisions, but not exactly in collisions, might have a high cost because they're also undesirable. And also, poses where the robot reaches singularities will also have a high cost. Now, in terms of transitions, what we want to do is penalize large moves. These large moves can lead to wild motions or discontinuities, so we want to discourage them. So anytime that we have a joint configuration in layer L and node M that lead to a new joint configuration on a new layer and a new node that is greater than some tolerance, that's what we want to penalize. These are moves that generate high acceleration for high inertia joints. The high inertia joints are the big joints that you would find at the base or at the shoulder. They're heavy, they're carrying all the weights in the robot. So once you start moving them, they have a lot of mass and can generate both the high acceleration and the high inertia. What they end up doing is they lead to end-tool motions that are wild and disruptive. So if you've ever worked with a real robot and you're learning about kinematics, you'll have experienced very wild moves from the robot as it tries to follow a trajectory with inverse kinematic solutions. So all of this would have high costs, and we would also penalize anything that is a wrist flip. Sometimes as you try to follow a path, the robot might reach a joint limit. And in order to continue along that path, it might be forced to flip around 359 degrees very quickly to continue on that trajectory. These are also very dangerous moves. So all of these motions would be high cost in terms of transitions. So as you can see, different optimal paths can result depending on the strategies that we assume for providing costs. Really, these are up to you, and what we presented on this slide is a very simple perspective on how to generate cost for these motions. You are the ultimate designer and can change the way we assign costs depending what you want to optimize. And so this graph technique then helps us to generate sequences of joint space poses. So let's see how we can actually compute the cost. So let's say we need to start with the final layer and give each node a cost to go. So you start with layer 6, and in order to compute some of those costs, you move back one layer to layer 5. Now we know that for each of these nodes in layer 5, we have 2 possible transitions. That's because layer 6 has 2 nodes. So we call this N61, and this node here N62. So if we want to compute the cost to go at this node 5.1, it would be done as follows. We would take the transition cost from 5.1 to the first node and then add any cost of that actual state. And then basically you take the minimal cost, whether it's this motion right here or this motion right here. After you finish the first node on layer 5, you go to layer 2, node or row 2, row 3, row 4, row 5, and compute all the costs for nodes in that layer. After we do that, we move to the previous layer once again. The optimal path in a given layer is found by following the lowest cost or the steepest gradient of cost for that layer. Let's look at a simple numerical example to clarify. So here we have a 5-layered graph, and basically we're going to start with the nodes here on the back. Okay, and these numbers found next to the transitions are the transition costs. So for us, moving from H to J incurs a cost of 1. Moving from H to K incurs a cost of 2. Moving from I to J incurs a cost of 3, and moving from I to K incurs a cost of 2. So once we have computed these costs, we want to take the transition with the minimal cost, or the cost to go that has the minimal number. So in this case, it'll be 1 for H to J, and it'll be 2 from I to k. So we see that here. So then we move to layer 3 and we repeat. In order for us to go from layer 3 to layer 4 using node E, the cost to go here would be 2, and the cost to go here would be 5. So 2 is the motion with the lower cost. That's what we would take. And then from F to H, we have a cost of 2 plus 1 equal to 3. And then from F to I, we have a cost of 2 plus 2, which would be equal to 4. So we would take the one that is 2 plus 1, which is equal to 3. So we would have these solutions, and basically we will repeat again for layer 2. Here we have a cost of 3 plus 2, 5, 1 plus 3, 4, and 4 plus 2, 6. So you could see then that we have this cost of to go of 4 at node B. And finally, we compute these costs, 6, 5, and 3. And so the best way to move through this path, of course, is taking this cost of 5 and then taking that cost of 4 from C to E, and then taking this cost of 2 and then taking this cost of 1. So this optimal path computation can be done in the Joint Space Planner package. And this package right now, we're assuming that all dangerous poses have been removed from the network from a collision planner. So all the state costs are set equal to 0. The transition costs are computed as follows. We do the sum for the different nodes in a layer times the weight of a particular transition, which is defined as a delta Q squared. Okay, so this delta Q represents the joint angles for the robot. The delta Q is the change in joint angle configuration. So these weights can be assigned differently for, as we looked in principle before, the transitions that have large moves will have higher weights and then penalize them. And then we take the square just to deal with negative numbers. So the joint space planner will look at the entire network and use the vector of joint weight to return the optimal path. In this example, the network is represented as follows. We have for each layer as an eigenvector. Okay, so all the nodes in a layer are represented as an eigenvector. But then sorry, let me repeat that. Each of these nodes represents a different IK solution. So this vector right here would be a vector of IK solutions. Then we have a vector of vectors which represents this plane. So these are the IK solutions at different waypoints. And finally we have the depth right here, which is a vector of eigenvectors, which represent these numbers right here represent the joint angle configuration of the robot. Okay, so this planner can adapt to an arbitrary size. You could have as many IK solutions as needed for a given waypoint, and you could have as many sampling points to reach your goal location, and you can save values for whatever numbers of joint angles for a robot, but you gotta be careful of the network size, as this too can explode. The package currently doesn't consider collisions with self or the environment, so that's one of the limitations. For the example that I ran before, where we have the 7 degree of freedom robot moving along a Cartesian path, when we use our generic planner, it samples every 5 centimeters or 0.1 radians. We get about 61 sampling points. We're solving between 130 and 285 IK solutions per waypoint. What this ends up looking like in a i7 CPU with one core operation is planning of 8 seconds. Of course, this is not ideal. It's not real time. But this is just for illustration of how a technique like this might work. Of course, this could be optimized by using more threads or using a GPU server or doing further optimizations. The way that the 8 seconds is broken down into is that 3 seconds of those 8 are used to find all 13,000 inverse kinematic solutions, and then 5 seconds are used by the dynamic programming algorithm to compute the minimal cost path. So I hope that this overview of a joint space planner using dynamic programming has been interesting to you and figuring out actually how do we go about finding the smoothest sequence of points across the waypoints. And 13.3, we're going to then look at how to integrate that with ROS. Thank you.